The Distributed Lock Manager is a resource synchronization subsystem designed to coordinate mutual exclusion across networked nodes. The system maintains lock state through a centralized registry and distributes lock grants via consensus messaging. All operations are idempotent and include explicit timeout handling to prevent deadlock conditions. The primary interface exposes acquire, release, and refresh operations. Lock ownership is tracked by node identifier and session token. Internal state transitions follow a deterministic finite automaton model. Lock acquisition follows a request grant acknowledge protocol. The client submits an acquire message containing the resource identifier, requested lock mode, and a unique request token. The server validates the request against current lock holders and conflict resolution rules. If the resource is available, the server sends a grant message with an expiration timestamp. The client acknowledges receipt, completing the three-way handshake. Unacknowledged grants expire after a configurable interval. Lock modes are classified into two categories, exclusive and shared. Exclusive mode prevents all concurrent access. Shared mode permits multiple concurrent readers, but blocks exclusive writers. The conflict matrix defines which mode combinations are allowed. When a lock request conflicts with an existing lock, the request is queued in priority order. Queue processing follows FIFO discipline with priority-based elevation. The server maintains a separate queue per resource to manage concurrent requests efficiently. Lock expiration is controlled by the lease duration parameter, which defaults to 30 seconds. The server decrements the lease counter at fixed intervals. When the lease reaches 0, the lock is automatically revoked and removed from the registry. If the client needs to extend the lock, it must send a refresh message before expiration. The refresh operation resets the lease counter to its initial value. Refresh messages include the current lock token for validation purposes. The release operation is straightforward. The client sends a release message with a resource identifier and lock token. The server validates that the lock is held by the requesting client. Upon validation, the lock is removed from the registry. The server then processes the first waiting request in the queue, if any requests exist. A release acknowledgement is sent to the client. The entire operation is atomic and non-blocking from the client perspective. Deadlock prevention relies on timeout mechanisms and mandatory lock ordering. Clients are required to acquire locks in a defined global order to prevent cyclic wait conditions. Each acquire request specifies a timeout value that the server respects. If the client does not receive a grant within the timeout window, the request is automatically cancelled. The server returns a timeout notification to the client. Subsequent retries reset the timeout counter. The lock state machine defines 4 states: available, granted, waiting, and expired. From available, a valid acquire request transitions to granted. If a conflict exists, the request moves to waiting. From waiting, the request either transitions to granted when the blocking lock releases, or to expired if timeout occurs. From granted, the lock either transitions to available through release, or to expired through lease timeout. State transitions are logged for audit purposes. The conflict resolution matrix is a two-dimensional table indexed by lock mode pairs. The entry is true if both modes are compatible, false if they conflict. Shared mode is compatible with other shared locks but not with exclusive locks. Exclusive mode conflicts with all other modes. The matrix is immutable and compiled at server startup. Lock compatibility is checked before granting any new request. The evaluation is performed in linear time relative to the number of existing locks. The message protocol defines fixed-width binary frames for all lock operations. Each frame begins with a 4-byte opcode field identifying the message type. The opcode is followed by a 2-byte length field indicating the frame size in bytes. The timestamp field records when the message was generated. The checksum field contains a CRC32 value computed over all preceding fields. Frames are transmitted via TCP connections with automatic retry on network errors. Session management is performed through opaque session tokens issued during the initial connection handshake. Each token is a 64-byte value generated using a cryptographic random number generator. The server maintains a session table mapping tokens to client identifiers and state information. A session remains active as long as at least one lock is held by the client or the idle timeout has not been exceeded. Idle timeout defaults to 5 minutes. Expired sessions have all associated locks forcibly released. The wait for graph is a directed graph, where nodes represent lock holders and edges represent waiting requests. An edge from node A to node B indicates that A is waiting for a lock held by B. The server periodically runs cycle detection to identify potential deadlocks. If a cycle is found, the server breaks it by revoking the lock of the youngest node in the cycle. The revoked lock is released and the lock holder is notified via an exception message. Persistence is achieved through write-ahead logging to a local journal file. Before any state change is made in memory, the change is written to the journal. The journal is flushed to disk at intervals determined by the flush policy. Synchronous flush is available for critical operations at the cost of increased latency. Asynchronous flush allows batching multiple operations before disk write, reducing overhead, but introducing small recovery windows. Error handling is specified through exception codes returned in response messages. A code of 0 indicates success. Non-zero codes indicate specific failure conditions: timeout, conflict, invalid token, lock not found, and permission denied. The server includes a descriptive error message in a response for diagnostics. Clients must handle all error codes appropriately. Some errors are transient and may succeed on retry, while others indicate permanent failures. Performance tuning involves configuration of several parameters. The least duration determines how long locks persist without refresh. Shorter durations reduce stale lock duration but increase refresh traffic. The queue processing interval controls how often waiting requests are evaluated. Shorter intervals improve responsiveness but increase server load. The flush policy affects write latency and disk I/O volume. Default settings are designed for balanced performance across typical workloads. Monitoring and diagnostics are provided through a statistics interface. The interface exposes counters for acquire requests, successful grants, timeouts, and expired locks. Per source metrics track average wait time and lock holder count. Per session metrics track active locks and total operations. These metrics are accumulated in counters that reset at configurable intervals. The statistics endpoint returns data in a structured binary format compatible with standard monitoring systems. Recovery procedures are initiated when the server restarts. The journal is read sequentially from the beginning. Each logged operation is replayed to reconstruct the in-memory state. Once replay completes, any locks with expired leases are revoked. All waiting requests are re-evaluated against the reconstructed state. Session tokens remain valid if the client reconnects within the recovery window. Failed clients are marked as disconnected and their locks are released after the timeout period.